So welcome to Unit 6. In Unit 6, we're going to look at ways to use cryptography to solve a wide range of problems. In Unit 5, we focused all on using cryptography to solve the traditional problem of authentication and then communication with secrecy and integrity. What we're going to look at in Unit 6 is different kinds of problems we can solve using cryptography. The first thing we'll look at is anonymous communication, and we'll learn about how to use a chain of asymmetric encryption to enable two parties to communicate over a network without anyone knowing that they're even talking with each other. Then we'll look at how to do voting, and there are lots of issues with voting. We won't get into all of them, but we'll look at the issue of, can you provide an accurate tally, know that each vote is counted, without revealing who voted for whom. This will also be done using a chain of asymmetric encryptions, but with some added features to ensure that the vote tally is correct. Then we'll look at ways to provide digital cash, a way to represent and transfer value similar to paper cash that can be done all with cryptography. This will involve introducing some new techniques. We'll look at a centralized way of doing that, which can be done using a new technique called blind signatures. And we'll also look at a decentralized way of doing that doesn't require any trusted authority, but uses proofs of work to create value. And this is what the Bitcoin network does. This is just a small sampling of the kinds of things that you can do using cryptography. All of these can be used just using the tools we've seen in this class, and we'll see ways to use asymmetric cryptography in many different ways in these examples. We'll also see ways to use symmetric cryptography, including hash functions, as well as one-time pads. So last unit we talked about HTTPS, how to use the transport layer security protocols to first do a handshake to agree on a secret key, and then to have a secure channel between a client and a server. What these messages are, we just drew as arrows, but what they really are, if we think about the internet, well, they're messages going through routers on the internet. And there may be many hops between the client and the server. And along these hops will go packets. Because they're using TLS, part of the packet is the encrypted message, but another part of the packet is the routing information. This is necessary so R1 knows the direction to send the message. It needs to know that the goal is to reach the server. So any eavesdropper who can see one of these messages, and it could be the first one from the client to the first router, or maybe she's intercepting a message on some later routing path, well, she can learn that the client and the server are talking to each other. This is a form of traffic analysis where the important property we want to hide is not the contents of the message, which, if HTTPS is working correctly, are encrypted and cannot be understood by Eve. But what we really want to hide is the fact that this client is talking to this server, or that Alice is talking to Bob. The mere presence of communication between two parties is often enough to cause problems. An example would be if the client is a dissident in some oppressive country and is connecting to a server that's used by dissidents to communicate, or a server in another country that's viewed as a threat. So if we want to prevent this kind of traffic analysis, we want to prevent adversaries who can observe messages on the routers from being able to know which parties are communicating, we need to do something else. So let's think of a simple example first. Suppose I want to send a message to Alice. If I just want confidentiality, well, I can put that in an envelope, seal the envelope, and write that it's for Alice. And to make sure my seal is good, I'll make sure that no one else can open this. And I could give the message to Alice. Now the problem is, if Bob is jealous and the mere fact that I'm communicating with Alice would cause problems, well, I can't just hand the message to Alice. That would show that we're communicating. What I'm going to do instead is use Colleen. I'm going to give the message to Colleen and ask Colleen to give the message to Alice. So I will have a new envelope. I'll give this to Colleen. And what I'll put in that envelope is the message I want to give to Alice. And this also has a very secure seal, so no one else will open the message. And I give it to Colleen. If someone sees me giving a message to Colleen, well, there's no problem there. Colleen would open the message and see that it's got a message to give to Alice. And then she could give the message to Alice. So this works a little bit, and Colleen could open the message and give it to Alice. So how well does this scheme work? So the question is, which of these properties are necessary for the scheme that I just described to successfully hide the fact that I'm communicating with Alice? Requires complete trust in Colleen. It requires that Bob cannot see when I talk with Colleen. It requires that Bob must not be able to see when Colleen talks with Alice. It requires that Bob must not be able to see both communications, when I talk with Colleen and when Colleen talks with Alice. The answer is it requires me to completely trust Colleen. Colleen knows that I'm giving a message to her, and she can open that message and know that it goes to Alice. It doesn't require the first one. If Bob sees me talking with Colleen, presumably that's not a problem. It doesn't require the second. If Bob sees Colleen talking with Alice, that's also not a problem. If Bob sees both of those and sees them in quick succession, especially if he sees the envelopes being handed on, well then he's got a good reason to suspect that I'm talking with Alice. So we need both of these properties. We need to know that Colleen can be trusted, and we need to know that Bob can't see both of these transactions. Those are pretty high security assumptions. We don't want to have to trust Colleen completely, and we don't want to rely on the fact that Bob can't see these two conversations. So the way to make it more secure is to add a third person. Let's say we know Edgar as well. And now, instead of giving the message directly to Colleen, what I'm going to do is take the envelope for Colleen, put that inside an envelope for Edgar. We need to fold things a little to make them fit. And now I'm going to seal this envelope with a very secure seal that only Edgar can open. So now I'll give this envelope to Edgar. Edgar will open it, see that it has a message for Colleen. Edgar will give the message to Colleen. Colleen will open that, see that it has a message for Alice, give the message to Alice, and Alice will open the message and see that she shouldn't eat the onion. This has more protection. Now Colleen doesn't know that I'm communicating with Alice because the message is going like this. It's going first to Edgar, then to Colleen, then to Alice. So neither Edgar nor Colleen knows that I'm communicating with Alice. Edgar knows that I'm sending a message through him that goes to Colleen. Colleen knows that she's receiving a message from Edgar and it's going to Alice. Neither one knows both endpoints. If we add enough hops, this can start to be quite secure. And this is actually called onion routing. That's why the message is to not eat the onion. And the name comes from the idea that an onion has all these layers. And as you peel off the layers, you get deeper into the onion. So doing this with envelopes would be pretty painful. We want to do this with math. So how do we do this with cryptography? So now Dave wants to communicate with Alice without anyone being able to know they're communicating. And we have a set of routers. These are like our friends in the example of the envelopes. And let's say I know about 5 routers. We'll call them R1, R2, R3, R4, and R5. And the routers are all connected. They can all talk to each other, and they can all talk to Alice, and they can all talk to me. So we're assuming we have a fully connected network here. And I haven't drawn all the connections because that would get kind of messy. So we'll assume we have a fully connected network here. And we don't need to have a physically fully connected network. There could be other nodes in between these. We're assuming we have secure channels between each of the routers. And we could set up those channels using TLS. So we have these secure channels between all of the routers and between all the participants, including myself and Alice. So we'll select some random sequence of the routers. Each of these I values is one of the values that identifies a router. And I'm going to send a message into this network. Let's assume for now that the last router that I select is R4. I want it to be the case that R4 sends the final message to Alice that Alice can read. The question is, what message should R4 receive? The answers are encrypted with Alice's public key, the message to Alice in clear, concatenated with the message, this is the message Dave wants to send to Alice, encrypted using the public key of R4. Encrypted using the public key of R4, the message to Alice, concatenated with the message encrypted with Alice's public key. Encrypted using the private key of Bob, the message to Alice, concatenated with the message encrypted with the public key of R4, or the message to Alice concatenated with the message encrypted with the public key of Alice, all encrypted with the private key of Bob. The answer is the second one. R4 is receiving this, so it better be something encrypted with a key that R4 can decrypt. R4 should not be able to decrypt something encrypted with the public key of Alice. R4 could decrypt these two, because R4 could know the public key of Bob, but then anyone could also decrypt these two. So we want it encrypted in a way that only R4 can open. That's like the envelope with the seal that only a particular person should be able to open. The content needs to be visible to R4 where to send the message next, which is what the to Alice part does, but invisible to R4 what the actual content is. Alice looks different from the other routers the way I'm writing it here. For this to be secure, there shouldn't be any real distinction between R4 and Alice. That's hard to get in a network like this. So it probably is the case that R4 actually learns that Alice is the endpoint, but because the message was received from the previous one in this chain, doesn't learn that it was Bob talking with Alice. So the question is, what message should Bob send to R2, the first link in the chain? Here are the possible answers. Check the one that would be best. The third one is the correct answer. The first one wouldn't work. R2 couldn't decrypt this message and wouldn't know where to send the next hop. This one would work for the first hop. R2 would decrypt it, know to send it onto R5, but then when R5 receives it, it wouldn't be able to decrypt this message and know where to send it. It's also unnecessary to have this extra decryption using KUR2. This outer message is already encrypted using that public key. So anyone who can decrypt this message can also decrypt that one. So there's no value added by having this encryption. The third one is the best answer. Here we're sending the message encrypted using R2's public key, so R2 can decrypt it. It has the next routing hop in plain text in the message that R2 can decrypt. And then it has the rest of it encrypted using R5's public key, so R5 will be able to decrypt the next hop and learn that that should be sent on to R4. The problem with the fourth choice, it would work for this hop, but then when R5 decrypts it, it wouldn't know what the next hop is. The final option wouldn't work because R2 would get the message to send to R5 and send the message here, which is M4. That's encrypted using R4's public key. R5 wouldn't know where to send the message. So the only one that works is the third choice. So in general, for onion routing to work, we need each message in the chain to be the message that's sent to the router RIK. It's going to be a message encrypted with that router's public key. It will have as its contents something explaining the next destination, as well as the message that should go to that next destination. And we can wrap as many layers as we want. The more layers there are, the more hops we go through, the less risk there is that all of the links in the chain can collude, or that a party can observe all of the communication and learn what's being communicated. So now the question is, suppose an eavesdropper can listen in on this link and can listen in on this link. So it has a way to listen on the outgoing links from me and the incoming links to Alice. Can they determine that we're communicating? No. Yes, if there's no similar traffic on the network. Yes, if there is a way to correlate message 1 and message 2. And yes, if the adversary can see all the traffic on the entire network. So I think the best answers are the second and third. No is hardly ever a good answer to a question about is there any possible way to break something. The way the adversary would learn that Dave and Alice are communicating is if there's a way to match up the messages at the endpoints. So this would be the case if there's no other traffic that looks similar on the network. These messages aren't the same. Remember that they're encrypted in different ways, that this message will not look similar to message 1, but they'll both be encrypted messages. They might be similar because of the length. There might be things the adversary can do to adjust the timing. Remember, this is not a direct link, so the adversary, if there are many messages going between Alice and Bob, could introduce delays in the messages and see the same pattern of delays on the outgoing messages. That would work if there weren't any unpredictable latencies inside the network. So if there's any way for the adversary to correlate those incoming and outgoing messages, then the adversary would know these two parties are communicating. If the adversary can see all the traffic on the network, this would be a very powerful adversary. Well, that's not enough unless they can correlate it. So even if an adversary could see all the messages coming in R2, if there's many other messages coming into R2 at the same time and many other messages going out of R2, if the adversary can't connect the ones coming in with the ones coming out, well, then they wouldn't be able to follow the chain. So in order for this to be secure, we need to know that there's a lot of other traffic on the network that looks similar. So you'd like to know that between all of these routing points, there's always messages going. They look similar lengths, similar timings. There's no way to correlate the messages that come in to one router with the messages that go out from another one. So this is one of the things that you need to do to make a network like this secure, is to make sure that there's enough traffic. You can inject a lot of fake traffic. That's expensive. You're wasting bandwidth on things that don't go. And you've also got to be careful to make the fake traffic look like real traffic. So you can't just send random packets If there aren't correlations between those packets, and if you're not sending a full flow, well, then that could be detected by the adversary. So there are lots of hard problems to solve to make this secure. There's a very successful project that provides this as a service on the internet. It's called Tor. You can download it as an extension to your web browser. It provides a way to connect to a website without revealing to the website where you're connecting from. You need to get a response as well. And so that means in addition to selecting the route for reaching the website, you need a route for returning. You don't want to include your IP address, so that would reveal your location in the response, but you want to get the responses. So what this does is select routes in both directions. Selects a random set of routers to reach the website that you want to communicate with, as well as a way for that to send a response along another random path. So I have one more question about this, which is an important question about whether or not this can work effectively. And the question is, how does a client who wants to use Tor to communicate anonymously know that set of routers as well as the public keys to select a path? In order to send messages, the first step is to select a random set of routers. So here's some possibilities. Select the one that you think would work best. So the closest thing to a correct answer here is to download the set of routers from a trusted directory. This has some pretty serious drawbacks, though. The other choice as well, asking Alice, if Alice actually knew everything, could work, but not everyone can ask Alice. Using SSL certificates would be a good way to get the public keys, starting from some root certificate authority to validate the public keys of the routers. And that could be used as part of it. That doesn't tell you what the routers are, though. We need some way to identify the actual routers as well as their public keys. We could send messages to random nodes. This would work if a large fraction of the nodes on the internet were Tor routers. We could also require that every router implements Tor. This would be great, but is not very practical. So what actually happens is that there's a list of known routers on the network that can be downloaded from a trusted directory. There's a big problem with this in that someone who wants to censor anonymous communication, which a regime that someone is using Tor to get around might well want to do, can also find these nodes. And the censor can download the trusted directory as well and block all traffic to those nodes. So this is a big challenge for networks like Tor to figure out ways to distribute the routers that is accessible and can be used by people that they want to use it to communicate anonymously, but isn't visible to a censor that would want to block all of those routers. There's no known great solution to this, but I would encourage an open discussion on the forum about ideas you might have how to solve this. The next topic I want to talk about is voting. Voting involves lots of cryptographic issues, and there are many interesting security properties that a voting system should provide. One property that many voting systems desire to provide is anonymity, that it shouldn't be possible for an adversary to know who someone voted for. The other property a voting system should have is that the count is verifiable. These are sort of in opposition. Verifying the count would be easy if each voter would be willing to publicly declare their vote, and someone could look at all of those votes. But if we want to keep the votes anonymous and have a notion of a private ballot, well, then verifying the count becomes more challenging. Another property some voting systems want to provide is coercion resistance. What this really means is that a voter can't prove who they voted for. If votes are secret and there's no way to prove for whom one votes, well, then there's no way to coerce a voter into voting a particular way. And then we have all the usual goals of reliability and security. These things are hard to achieve. There are good ways to achieve them with paper ballots if we have trusted ballot boxes guarded by trusted election officials. And if we have enough trusted third parties, well, maybe we can trust them to report the right tally. We're going to look at one interesting cryptographic way to do voting, but I want to emphasize that this is not a solution to the real problems that are necessary to run an election. But it solves this issue of can you keep votes anonymous and still have a way to verify that the count is correct. So here's the idea. You collect the votes from the voters. Those are inputs to a random permutation. Let's say this is controlled by the Apple party. And what the permutation does is randomly scramble the order of the votes. So now the position of the votes that came in doesn't match the position of the votes that came out. We also do some encryption, and we'll get to that in the next question part. And those are passed along to the next party. Let's call that the blue party. The blue party also scrambles the votes in some random permutation. And then those are passed along to the next one, and we'll call this one the crazy party. So our parties start with the letters A, B, and C. And the crazy party does the same thing. It selects some other random permutation, or it randomly selects a permutation, and it scrambles the positions of the votes. So in order for this to work, we want at the end of this to know what the actual votes are. The question is, what value should we use for X to enable this chain? And our security assumption is that the apple, the blue, and the crazy party all hate each other, that they wouldn't possibly collude, so they can be trusted not to collude with the other parties. But otherwise, they can't be trusted. They want to try to change the election, change the votes, do everything they can. So the question is, which one of these would be the best choice for the xi values? And neither of these is a correct choice. Neither of these will work securely. We're going to have to do some other things. But which one of these is the best starting choice? The answer is the second one. We need to be able to unravel the layers of encryption as we pass the vote through the network. So that means we need the last step to be encrypted with the public key of C. So C can decrypt it and get the actual vote. The previous step should be encrypted with the public key of B, and the first step should be encrypted with the public key of A. This idea is called a mixnet. It was invented by David Chaum. And you'll notice that this is quite similar to onion routing. And in fact, onion routing was based on this idea. There's a couple issues we have to work out, though. This kind of encryption won't work very well. There's some big problems with the way we've described it so far. So suppose that we do this and we encrypt this way. How well would this actually work? If we encrypt the vote as described, we're going to use the layered public key encryption. And the vote is the name of the party the voter wants to vote for. And you can assume that the encryption is done using RSA, where the public keys are well known to everyone. The private keys are kept secret to their correct owners. And there are no vulnerabilities in RSA. The answer is it doesn't work very well. So the reason for this is that anyone observing these messages, given that there's only a small set, well, you can compute this value, given the public keys of C, B, and A. You can compute the value of xi for the three possible votes, match that up to the incoming votes, know exactly what they are, so there's no anonymity for the voters. So either A or an eavesdropper could do this. The second choice is a little more ambiguous. C could output any votes it wants. There's nothing that verifies the votes that C outputs. But in this case, because the encryption is broken, someone looking at the votes that come in knows what the votes are already and knows if C cheats. But there's no point to the mixnet if this is what we do. So we need to do something different. This by itself is not going to work. What we need to do is add some randomization to our encryption. So the first idea to solve this is just to replace the vote with a vote concatenated with some random value selected by the voter and kept secret. So the question is, does this work? And we're only worried about protecting the voter's identity here. We're not yet considering the problem of can C fabricate votes at the end. So the answers are yes. Only if the eavesdropper cannot intercept messages on both this link and this link. Only if the interceptor can't intercept all the messages along the whole chain. And only if the eavesdropper doesn't collude with C. The answer is the fourth choice, that this works at least against the attack that was described, as long as the random value is kept secret. If C decrypts the message, well, C has the private key here, so we'll learn the random value and can use that in collaboration with the eavesdropper who heard these messages now to figure out which voter voted for which candidate. So this is a weak system. So this solution doesn't work, at least not if our threat model includes an eavesdropper colluding with party C, or C having the ability to eavesdrop on this link. So this isn't good enough, but we can carry that solution through and add random nonces to each of these layers. So that's what we're going to do. The inner message will be the vote concatenated with a random nonce, encrypted with C's public key. The next layer will be that message concatenated with a new nonce and encrypted with B's public key. And the outer layer will be encrypted with A's public key, will be this message concatenated with the third nonce. So this is the message the voter sends with that voter's vote. Party A will decrypt the outer layer, randomly permute, send the result to B, who will decrypt B's layer, randomly permute, and send the result to C, who will decrypt the final vote. As a first step to validating the votes, instead of just publishing the V values, we're going to require that C also publish the R0 values. So the final tally will be a list of votes and their associated nonces. This means the voter can check that the nonce that the voter uses in that list. So if we use this protocol, which of the three parties, Apple, Blue, or Crazy, would you rather be? So it looks like Crazy definitely has the most power here. Crazy publishes the final votes. Crazy could decide not to include votes that aren't for the right selection. Crazy could tamper with the votes. The one validation we have is the voters can check that there are votes in that list. So Crazy can't add extra votes if the number of votes in the beginning is known. Crazy could replace some votes, change those votes, and there's no way with this scheme yet for a voter to prove that Crazy cheated. If the voter can prove that Crazy cheated, well then maybe it's not such an advantage to be Crazy. So is there a way for a voter to prove that their vote was not included? So if what C publishes at the end as the tally is pairs of votes and the associated R0 nonces, how can a voter prove their vote is not included or was corrupted in the final tally? The answer is they could reveal all three of their nonces, show that they compute the correct xi value. Assuming the encryption function has the properties it should be difficult to find R0, R1, and R2 values that encrypt in the same way with a different vote. Note that this requires the property of the encryption function, that it's hard to do this by cheating by finding a different vote with different nonce values that encrypts to the same thing. This is actually a required property of encryption. As long as the encryption is invertible, this would be impossible. If we could find two such values, well then we couldn't decrypt and get the same X or Y out correctly that went in. So that's why this works, that if we're willing to reveal these values and show that they produce xi, that proves that someone somewhere along the chain cheated if the vote's not recorded in the final tally. The big drawback of this is it requires that the voter reveals her vote in order to show that her vote was not included in the tally. So the other approach for solving this is what's known as an auditing mixnet. And the idea here is that each participant in the mixnet can audit some of the outputs of the next step. So to do that, we need to provide extra inputs. So instead of the voter just providing the vote as encrypted to party A, they'll provide it to party B as well. So all of the incoming votes go to the next two steps. And now B is going to audit A. And it does that by picking some random set of inputs. So let's say it picks this one, and it picks this one, and it picks some of the ones in here. So that means it's looking at some of A's outputs, and we'll call these Y values. So this would be Y2, this would be Y something else, and this would be Y of n minus 1. All right. And this would be Y of n. So for each of the n inputs, Bob picks some number to audit. And what B does is ask A to prove that Y2 is a valid input. In order to prove this, what does A need to provide? So what must A provide to B in order to prove that Y2 is a valid output from A's mixnet? The answer is the third choice, and it's really only necessary to provide the nonce, but it's helpful to provide the K value as well. And what B needs to check, once this nonce is provided, B can check that the encryption using A's public key of the output, which is the Y2 value, with the nonce added, that was the part that Alice removed. So what Bob needs to do is check that that output is equal to X of K. And that value was provided directly to B because all of the inputs from 2 links ago went into this mix as well as the outputs from A. So this proves to B that for the particular output that B asked for, that corresponds to one of the inputs to A. And we can do the same thing all the way down the chain. That means that A will provide its outputs both to B and C. C will be able to verify that B did the mix correctly by picking some random ones and having B prove that they're correct. And at the final stage, B will provide its outputs to C as well as to some validator who can validate that C did the correct thing. So this audits one output. How many should we actually audit this way? So usually when people talk about auditing, the more is always better. The more auditing you can do other than the cost of it, the more you have a likelihood of catching cheating. But in this case, that's not the case, that we have to be careful. If we audited all the outputs of the mixnet, well, then that would reveal exactly what the permutation was. So we have a trade-off here between voter anonymity and catching cheating of the mixes. If we just audited one output, the chances of catching cheating would be too low. If there's n votes, a mixnet could cheat on half of them with only 1/2 probability of getting caught. This is much too low. It's probably not necessary to cheat on half of the votes. The last step can see what the actual votes are and decide which ones to cheat on. So cheating on a much smaller fraction than 1/2 and getting caught with a much less probability than 1/2 would make that risk worthwhile in many situations. So suppose there are 100 votes and 20 are audited. What's the probability that a mixer can cheat on 4 of the votes without getting caught? So the answer is 0.4. The way to think about this is thinking about how to choose the votes. So we have 100 votes to begin with. There are 4 that the mixer cheats on, and the auditor is sampling 20 votes in this space. So as long as the auditor picks one of the votes that was cheated on, then the mixer would be detected. So we can compute this by dividing the number of ways to choose without picking any of the cheated votes. So that's choosing out of the 96 non-cheating votes, divided by the total number of ways of choosing the votes. So to solve this, we just need to compute 96 choose 20 divided by 100 choose 20. Since the orders will cancel out, there are 20 elements each time, this is the same as computing 96 times 95 times down to 77 divided by 100 down to 81. We could cancel things out and compute this by hand. We could also just compute it all in Python. So here's a procedure to compute the product of a list, remembering to multiply by 1 point to turn this into a floating point so we get accurate division. And when we run that, we get the result 0.04 with some more. So we might like a higher probability of catching cheaters if we think cheating on 4 votes is enough to change the election. So we'd like to audit more votes. We can do that. That will increase the probability of catching a cheating mixer, but will also increase the probability that privacy is lost, that a vote can be traced through the mixnet. So here's the scenario I have in mind. We have 3 mixers. At each stage, we validate 1/5 of the votes, and we have to audit the last one. We don't have another mixer here. We need some designated output auditor that receives these outputs as well as these and audits the last one. So that's our 3-step mixnet. And at the end of this, some votes are revealed. And the question is if an eavesdropper who can observe messages along all of these channels and observe all of them can determine which voter cast this vote. The answer is 0.008. At each step, there's a 1/5 probability of seeing that particular vote at both stages and knowing how it was mixed. So in order to trace the vote all the way back, we need to see that same vote each time. So that would be 1/5 to the third, which is 1 divided by 125, which is 0.008. So that means there's a trade-off here. If you do more auditing, if you increased this from 1/5 to a higher value, that would increase the probability that a given voter could be identified. It would also decrease the probability that the mixnets could cheat without getting caught. So here we have a trade-off between the privacy of the voters and the likelihood of detecting cheating. The next major topic we're going to talk about is digital cash. What we want to do is find some way to use numbers to simulate something that would be similar, maybe better to, maybe worse than physical cash. So what are the properties that physical cash has? Or at least the properties we might want it to have. Well, it should have a universally recognized value. That means everyone agrees that it's worth something. It should be easy to transfer between 2 individuals. That means you can transfer it without having to talk to a bank or some trusted third party. Some might argue against this, including some governments, but many individuals would like their cash to be anonymous and untraceable. Not all governments want this, but let's assume that as an individual that we do want our cash to be anonymous and untraceable. We'd like it to be light and portable, easy to carry, and we'd like it to be hard to copy or forge. If someone can counterfeit the money, well, it probably won't have recognized value for very long. So assuming that we do want these 5 properties, which of these does US paper currency satisfy well? And I apologize for specifying US. I know many of you are not in the US and have different paper currencies. You can answer this for your currency. I'm going to answer this for what I think about US paper cash. It's definitely a subjective question, but we'll talk about what I think the right answer is. So US cash definitely has universally recognized value. At least in the US, essentially everyone accepts it. But even in other parts of the world, many people accept US cash. It is easy to transfer. You don't need to go to a bank or even interact with a bank in order to be able to transfer cash between individuals. It's sort of anonymous and untraceable, and I didn't check this one. It's definitely not designed to be untraceable, right? Each bill has a unique number in it, and you could trace that number. It's untraceable in practice because people don't tend to record those bill numbers, but it's not untraceable technically. And it's certainly the case when banks are robbed and there's a sequence of bills that were marked in the same order. Well, that's one of the ways those bills might be detected. It's not light and portable. The largest currency in the US is a $100 bill, and that weighs the same as a $1 bill, which weighs about a third of a gram. That means if you can carry 1 kilogram, that's only 2,740 bills, which would be over $250,000. Not a bad amount of money for an individual to carry around, but it certainly could become a factor if you're talking about large corporate transactions where 1 kilogram weighs $250,000. This is one of many reasons why very few large cash transactions are done, and you see scenes in movies where someone needs a whole briefcase full of money in order to do things. The last question, whether it's hard to copy or forge. And I think the answer to this is also really no, that it's just paper. The reason that it works is that the penalties for getting caught copying or forging are high. So the real answer is that it is hard to copy or forge in large quantities without getting caught. Enforcement of counterfeiting is taken very seriously. It's done by the Secret Service, that's also responsible for protecting the president. And the only people who can get away with forging US currency in large quantities are hostile countries where US law doesn't reach. One way to think about money is it's really a promise from a trusted bank. It's a promise that says, if someone brings this money to the bank will exchange it for something of real value. Today, we think of the paper itself as having real value. But in the early days, what the paper meant was you could go to the bank and exchange it for something that everyone recognized as real value. Say a bar of gold, almost as valuable as a gold star. So if that's what money means, well, then we should be able to do the same thing with cryptography. Let's see how that would work. So Alice would go to Indivisible Prime Bank, which everyone knows is very trustworthy, and she would give the bank $100 in some other currency. Let's assume the bank takes US dollars. So the bank will write a message that says the bank owes the bearer of this note $100. And the bank will send Alice a signed version of that message. So the message, along with its signature, which is signed by the bank, using the bank's private key, signing a hash of that message. So this signature proves that it's a valid IOU from this bank, and now Alice has something representing currency. Now Alice could spend the currency. She could buy some tacos from Bob's Taco Emporium, give him the currency, pretty expensive tacos, and Bob could take the note, this signed message from the bank, and give it to the bank and ask the bank to deposit it into his account. So now the question is, how well would this scheme that I've described work? And let's assume that everyone in the universe trusts indivisible primes and knows that bank's public key. So if this is true, well, then it does have universally recognized value. Everyone can check that signature and know it's an IOU from IP Bank. It does seem to be easy to transfer. You can just send the bits to another person. It could be anonymous and untraceable, and let's assume that it is. This would be the case if all the IOUs the bank creates are exactly the same. And the way we described it, it seemed like they are. It's very light and portable, so it looks like we're doing really well. We got 4 out of 5. We got a big problem, though. It's not hard to copy. It's in fact trivial to copy. We can send the same bits multiple times, and no one knows which ones are valid, which ones are copies. So this doesn't work. And once we've lost this property, well, we've lost this one as well. It is hard to forge. To forge it, we need to know the private key of the bank, but that doesn't matter because once we have one bill, we can make any number of copies of it and spend them as many times as we want. So this means it actually doesn't have the universally recognized value. Depending on how you interpret this question, This is what I think is the correct answer, but there are other ways to interpret this where your answer could be equally valid and correct and not match mine. So one way to solve this would be to give each bill a unique ID. And then if someone attempts to double spend a bill, the bank would check, has that bill been spent already? And if it's been spent already, the bank would alert the spender that it's not a valid bill. Well, this would also cause problems for the second possibility. It would no longer be easy to transfer if you have to check the ID with the bank every time you get a bill. It would also no longer be anonymous. It would mean the bank can track all the transactions because every time there's a transaction, the bank sees the unique ID and knows who is transferring money to whom. So our goal is to have unique IDs to prevent this copying problem, but preserve the anonymity and somewhat preserve the easy to transfer. We'll still need the bank to check the ID when the money is deposited, but maybe there could be transactions before that, and we can trace them back to who cheated at the point where the cheating happened. So that's our goal. The main tool that we need for this is a new cryptographic technique called blind signatures. The solution to this is a technique known as blind signatures. This gives us a way to associate a unique ID with a bill to be able to detect double spending, but doesn't allow the bank to associate the unique IDs on the bills with the person who acquires that bill. So here's the idea. Alice will deposit her $100 in the bank, and along with the bill, she'll generate a message that says bill number RA, some unique ID generated by Alice. Indivisible Prime's bank owns the bearer $100. And she'll go to the bank, give the banker the $100 bill, and ask the bank to sign the message M. To make it a blind signature, though, she'll insist that the banker wear a blindfold before bringing out the message M, and the banker will have to sign it without being able to see this message. And the bank will give that signed message back to Alice. This protocol has an obvious flaw in it. The bank doesn't know what it's signing, so Alice could deposit $100 and ask the bank to sign a message for $100 gazillion. When someone deposits that bill, the banker will no longer be smiling. The solution to this is a technique known as cut and choose. This is somewhat similar to what we saw in auditing for mixed nets, and it has lots of applications to other cryptographic problems as well. The way we would do that with this scheme is instead of just generating one message like this, Alice would generate a large number of messages, let's say 100 of them, send them all to the bank. The banker, who's no longer blindfolded or frowny, will randomly pick one of these messages. Let's say he picks message 38. We'll look at the other ones. Each one of those should have a message like this, but with a different random value. Check that they're all okay. If they're all okay, then without looking at message 38, then the banker will be blindfolded and sign message 38. The point of this is that Alice generates all the messages, transfers them to the bank, but the bank doesn't see them until the bank randomly picks one. Since the bank is picking the one to sign randomly and inspecting all the others, the probability of Alice being able to cheat without getting caught is 1 in the number of messages. So that could work with blindfolds. We'd have to be careful how we deliver the messages to the bank and then let the banker pick one and then see them without the blindfold. But that could work. Not very convenient though. So what we want to do is figure out a way to do this using cryptography instead of blindfolds. The scheme we'll look at for doing this is built on RSA, and it uses RSA signatures, as we've seen in Unit 4, but this time, instead of using them normally, we'll use them in a way that blinds the message from the signer. So here's the protocol. We'll assume Alice wants the bank to sign a message, and Alice knows the bank's public key. It's an RSA key pair with the exponent and a modulus. So M is the message Alice wants the bank to sign. Alice also picks a random value. We'll call that K. Next, Alice will compute T by multiplying the message by K raised to the EB power. If K is random, selected from the integers from 1 up to NB minus 1, and it's also relatively prime to NB, well, that would make K to the EB mod NB a permutation of the values in ZB. So that means that this is also random in that range. And so M multiplied by this is random. This doesn't reveal to the bank the value of M, so we can safely send that to the bank without leaking any information. And the bank will sign that message using its private key, its private exponent dB. That produces the value T to the dB power, mod N, which the bank sends back to Alice. So as far as the bank is concerned, it just signed a random value, and it sent that back to Alice. Is there anything Alice can do with this that's useful? So the question is, which of these is equivalent to the value produced by the bank? Here are the choices. To answer this question, think about the properties of RSA. The answer is this one. Here's why. So the signature is t to the db mod nb, and this was t. So that's what this is. We can use the property of exponents to simplify this. And now distributing the exponents, we get this. And here we have this term, k to the ebdb. Well, these are RSA keys. This is the public and the private key for that modulus. So that is the equivalent to what happens when we do encryption and decryption. So this is equivalent to k because these exponents end up performing encryption and decryption in the RSA system. They're designed so that's equivalent to 1. And so we get m to the db times k mod nb. Well, this value k, that was the random value selected by Alice. So she can just divide that out. And by dividing out the k, she gets m to the db mod nb, which is exactly what she wanted. That's the message m signed by the bank. Should we be worried that RSA has this property? The answer is we should. And this is related to the homework problem on Unit 4, where we saw that you could forge an RSA signature by multiplying two signatures. In this case, the message that's being signed might be used to produce other messages. So we need to be very careful when we output the result of RSA decryptions. We might be signing something different from what we think we're signing. So here's how this works in the blind signatures protocol. Alice will generate not one message now, but 100 messages, each one of this form, but with a different value for R1. Alice will also pick 100k values. Send all of those to the bank. The bank picks some random value x between 1 and 100 and unblinds all the other messages. So that means the bank will send x to Alice. Alice needs to send something back to the bank that the bank can use to verify that all of these messages, other than message x, contain something like this. So what should Alice send back to the bank? So the set of all the RI values, except for the one corresponding to message x. The set of all the KI values, except for the one not matching x. Both of these, or none of these work. The answer is sending all of the KI values would be sufficient. Those are the values that the bank would need to unbind the messages, because the bank can decrypt all the messages using its private key and then divide out the k raised to the EB power from the results. It would be okay to send this, but there's no need. There's no security loss in sending the RI values, except for the one for message x. But the bank's going to learn those anyway, since after it divides out the KI to the EB power, it has all of these values. So at the end of this protocol, Alice will be able to compute message x signed by the bank. So now Alice can spend the bill, give it to Kathy. Kathy can verify the signature, and she could deposit the bill in the bank. The bank checks that this ID has not been spent before and believes that it's a valid bill. If Alice spends the bill again, when Doug gives it to the bank checks the signature but finds that this RI value was previously used. So the bank knows the bill was double spent. The problem is the bank doesn't know who double spent the bill. The bank received the bills from Kathy and Doug, but they weren't the double spenders. They were the ones that were duped into accepting the bill. Alice was the double spender. And because of this blind signature scheme, the bank doesn't know that Alice is the one who spent the bill. So for this approach to work, we need a way to trace the double spent bill back to the person who double spent it. But we also want the bills to be anonymous. So that sounds like a contradictory property. There's actually a way to achieve this. There's a very clever solution to this that was developed by David Chaum and colleagues in 1988. So the key idea is that if the cash is only spent once, then it's anonymous. But if it's spent twice, then the identity of the double spender is revealed. So I want to see if you can guess how to do it. It uses cryptographic tools that we've seen before, and the key idea is to provide this property. So the answer is the one-time pad. If you can figure out a way to use any of these others to also do it, please post that in the forum. But certainly the easiest way to do this is to use a one-time pad. Remember that the key property we have with a one-time pad is that we can split a message into two pieces and XOR them to get the message back. That's what we're going to do here. So now we're going to use this in our blind signature scheme. Alice will create 100 messages like this, each one with a different random nonce. But what she's going to add to the messages is is an identity list made up of m of these values. We'll talk more about what these are in a second, as well as the usual value of the bill. What we want these I values to be are things that reveal Alice's identity if someone knows enough about them, but otherwise reveal nothing. So here's what they are. They're a concatenation of two hash values. H is a cryptographic hash function, where the property we want is that the two parts XORed gives you Alice's identity. And it's easy to create these values. We can set the first one to a random bit string, and we send the second one to Alice's identity XORed with the random bit string. So which of these would be the minimum amount of information needed by the bank to verify these messages all would be enough to learn Alice's identity if someone had both parts? The answer is the first choice. Alice needs to validate, the answer is the first choice. The bank needs to validate the hashes, so it needs to know the preimage for the hash. It's enough to get just one of those. It isn't necessary to get both of them, because the bank presumably starts knowing Alice's identity. If the bank doesn't start knowing Alice's identity, well, then anyone could create a bill that would blame Alice for double spending it. So if the bank knows Alice's identity, the bank can compute the other part of this, computing xk1 by XORing this value with Alice's identity, and then can check both of the hashes are correct. If they are, that validates that each of these identity components is correct. So now let's look at what happens when Alice spends a bill to see how to solve the double spending problem. So at the end of this protocol, Alice will have a message like this, where each one of these identity pairs is one of those pairs of hashes. To spend the bill, Alice sends the bill to Kathy, and Kathy sends a challenge back to Alice. And what the challenge is a list of m random bits. These will tell Alice which parts of the identity she needs to open. So in order for Kathy to accept the bill, what Alice has to do now is for each one of these, validate one part of the hash. So if Kathy's challenge bit was 0, what Alice has to provide is the 0 part of identity 1. And remember what identity 1 is the hash of the 0 part of identity 1 concatenated with the hash of the 1 part, where the property we need is that these two values XOR to Alice. If the challenge is 1, then it'll send the 1 part of the corresponding identity, and so on. So now Kathy can validate these hashes, so she's going to check that this matches the value sent by Alice, and we'll do that for all the identities. If they all match, Kathy accepts the bill. When she deposits it, she sends these I values to the bank. So suppose Alice tries to spend the bill again. This time she'll send it to Doug. Doug will do the same protocol. He'll make a challenge, send that challenge to Alice, get back the I values, but they'll be the ones corresponding to his challenge, and he'll do the same check before accepting the bill. And now Doug can deposit the bill, sending along the same I values. So now what does the bank have? Well, it has both parts of one of the I values, as long as one of these challenge bits is different. The bank knows there was double spending because it saw RK value twice. It also knows the identity of the person who obtained that bill, because it can XOR the 0 part of identity 1, which it received from Kathy when she deposited the bill, with the 1 part of that identity, which the bank received from Doug when he deposited the bill. So now the bank can tell the police to arrest Alice for double spending a bill. So to see that you understand all this, the question is, if Alice spends a bill twice, and m, the number of identities included in the bill, is 10, what's the probability that she gets caught? So that probability is greater than 0.999. And the reason for that is the only way she wouldn't be caught is if the two people she spends the bill with pick exactly the same challenge. The challenge is 10 bits long. So the probability that would happen is 1/2 to the 10th, 1 in 1,024. And 1 minus that is greater than 0.999. So that's pretty high. If that's not good enough, we could increase m. So the last thing I'm going to talk about this unit is Bitcoin, which is a way to do digital cash in a completely decentralized way. This means that there's no bank, there's no trusted authority, but everyone who participates in the protocol is considered a peer, and they all have an equal say as to what's valued and what's not. Bitcoin combines lots of ideas from previous protocols, but the particular way that Bitcoin does it was proposed by Satoshi Nakamoto in 2009. The way it avoids needing a centralized bank is to keep track of every single transaction that ever happens. So in order to track transactions, we have a chain of signatures. So here's how that works. Some coin comes in, and we'll have to talk about how that value gets created next. For Alice to transfer that coin, what she'll do is create a message that includes the coin, includes that she's transferring it to Bob, and she'll sign that with her key. So then she sends that to Bob. Bob can verify the signature. For Bob to transfer the coin, he'll add transfer to Kathy to that, and then sign the whole thing with his private key. And now Kathy would do the same thing, take everything that Bob sent, add a transfer message to it, and sign the whole thing with her private key. And then she can transfer it on to Doug. And every link in this chain, as long as they have all the public keys they need, can verify the entire history of transactions. So Kathy can verify the signature of Bob, open that up, verify the signature of Alice inside it, and verify that the original coin. So this is a way to use public key cryptography to keep track of an entire history of transactions. Does it provide enough to provide digital cash? So how many times can Bob spend the coin? The answer is as many times as he wants. There's no way when Kathy receives the coin from Bob that she can verify he didn't already spend it to someone else. So in order for these coins to have some value, they have to be scarce. It has to be the case that you can't spend them multiple times and you can't just create them. So this is where the peer-to-peer network is useful. So every time someone receives a transaction, they don't just accept it. What they do is they send it into the peer-to-peer network. So when someone wants to verify a coin, what they need to do is send it into the peer-to-peer network. Every transaction in that coin can be verified by all the other members of the network. And before the transaction is considered valid, we need to know that that coin hasn't been already spent in some other way. So there's two important parts to this. So that means all the nodes must agree on all the transactions. And that requires some sort of timestamp. Nodes are going to receive messages at different times. We need to know it's the case that if this coin was spent twice, that before this one validates the transaction, we need to ensure that if someone attempted to spend a coin twice, both transactions wouldn't be validated by having different parts of the network have different views of that history of all the transactions. So how do we provide this time step? And we need to remember that some of these nodes might be malicious. We have no way to know that all the nodes are trusted. Anyone who wants can join the network. We just need to have some honest parties to validate the transactions. But we need to know that dishonest parties can't invalidate the history of transactions. The key to this is requiring a proof of work. For each time step, we're going to have a new block, and we need to know that creating those new blocks requires work. If it requires enough work to increase the time step, then it's unlikely that a malicious user can increase the time step faster than the whole network. So how do we make that hard? We need some kind of proof of work to be embedded in the time steps. So here's a way to do a proof of work. In order to prove you've done some amount of work, you need to find a value of x where the hash of x starts with some number of zeros. Doing that requires work if this is a good cryptographic hash function. At least if we have a random oracle assumption about that hash function, the only way to find such an x value is to keep guessing and looking at the output. So you need to do the amount of work necessary to find that output. So how much work is that? So how many times do we expect to need to compute the hash function h in order to find a value of x where h of x starts with 0 to the 10, starts with 10 consecutive zeros? So the answer is 1024. If the hash is a good cryptographic hash and it produces a uniform distribution, the probability that any bit is a 0 is 1/2. And we need to find an output that starts with 10 zeros. Note that it doesn't matter how big the output of the hash function is. This is the same whether it's a 256-bit output or a 192-bit output. It doesn't matter how big the output of the hash function is, whether it's only outputting 10 bits or outputting a more reasonable number like 256 bits, as long as we restrict it to the first 10 bits having to be 0. So that means finding a hash value with certain properties is expected to require an amount of work, and by adjusting those properties, we can increase the amount of work. So this is what Bitcoin does. So in order to create a new block, which would validate the next history of transactions, it's necessary to find some value x such that the hash of the hash of the state concatenated with x is less than some target. You keep increasing the value of x until you find one that satisfies that property. And that provides the time step that allows a new block to be generated. So this is the idea Bitcoin uses to generate a timestamp, is you have to keep finding new blocks, and a block will validate a set of transactions. But to generate a new block, you've got to find a new timestamp, which is this target. So you've got to find a value where the hash of the state concatenated with that value. And the state does two important things. It includes information about the previous block. So this is how the timestamps form a chain, that the state must include the previous block. It also includes some information that's likely to be unique for each member of the network. This is how they avoid it being the case that they're all racing to find the same value x. So given those properties, then the goal is to find the value x that you can concatenate with that to be less than some target. And the value of the target controls how hard it is to find. And the way the Bitcoin currency is designed to work is this value of the target is adjusted in a way that makes the time to find x keep about 10 minutes. That's the time for the whole network to find the next value. So that value of the target will keep decreasing as the computing power in the network increases. And if you go to the Bitcoin website, you can see the current value of the target, which is this value, that in order to create a new block, you've got to find an x value such that this property is less than the target. And I should emphasize that these zeros are not just 1 bit. This is hex, so each one of these zeros is 4 bits. So you've got to find a value where the hash starts with 54 zeros, followed by something less than 1011 and more. So if you found a value that hashed where the result started with 55 zeros, or started with 54 zeros, a 1, 0, and a 0, well, then you'd be golden. You'd be able to create the next block. That would allow you to earn the value of a new block, which currently is 50 Bitcoins. Each Bitcoin is worth about $5. So finding a hash that hashes to this would be worth about $250. And the rest of the network can verify that. It can compute the same hash function, verify that for the x value that you found, the value is less than the target, and that will add that block to the Bitcoin network. So the difficulty of finding such hashes keeps decreasing. The reason it's so low is because of using GPUs. If you're using a regular processor, it would use far more than $250 in computing power to find such a hash value. If you have a GPU, there are algorithms for implementing the hash function more efficiently. That would mean that finding a value that satisfies this property should require about that much value in computing power. So to see if this makes sense, I want to ask why the timestamp function, the one here to find the next block, uses 2 hashes instead of 1. Here are the choices. See if you can figure out which one would make the most sense as to why there are 2 hash functions here. So the answer is to increase the amount of work required. Normally, we want to use computation to reduce work, but here the goal is to make this amount of work to find a Bitcoin to be stable, to be fairly predictable, and to be about 10 minutes long. And so we could do that with just one hash function by reducing the value of the target. That would require changing the target more frequently and using more 0 bits in the target. The alternative is to make it harder to compute each value of x, and that's what the 2 hash functions do. So now what happens in the network is at each time step, a new block is created that validates all the transactions in that block. At the point where this block is created, this has to be the longest blockchain. That's the way that Bob can validate that this was a valid spend. Someone could try to create an alternate blockchain. So if Bob wants to spend the coin twice, what Bob would need to do is create a chain that's longer than the longest chain. When a transaction is validated by the network, all the signatures in the coin are checked. This is using the transfer chain. But to prevent double spending, there's also a check of this chain of blocks. And the check is the longest chain is the one that's viewed as correct. So each peer in the network might see a different view of this chain of blocks. If they see different views, the one that has the longest chain is the one that will be viewed as the most correct view of all the transactions. So every participant in the network is effectively keeping track of all transactions. And the version of all transactions that people trust the most is the one with the longest chain. And if an adversary wants to create a longer chain with a different view of transactions, so if Bob wants to double spend this coin and say give the same coin to both Kathy and Doug, what Bob would need to do is create a longer chain that convinces Doug that this is the correct view of the network and this view is incorrect. So that requires finding these hash values. If the power of the network exceeds the power of the adversary, well, then it's likely the network will have a longer chain than the adversary can produce. And keep in mind, the motivation for producing this attack is just to be able to double spend one coin. There's still the chain of public key signatures that validates the transfers of each coin. So the resources that you would need to spend to produce a longer chain to convince someone that you didn't spend that coin in the other chain, which is now the one that would have included the previous spend, is to find these hash values quicker than the network can. The incentives are set up in such a way to make it unlikely that someone will want to do that, since if you do find the next hash value in the chain, well, you can create a new block, which is worth 50 Bitcoins. If you create a longer chain, trying to catch up to the chain that the network has, well, that's going to require a lot more computing resources and would only allow you to respend the Bitcoins that you already owned. So this doesn't provide anonymity in the traditional sense. It avoids the need for a central authority, but each transaction is known to everyone in the network. The way to provide some anonymity is instead of using your actual names in the transactions, you can have different identities for each transaction. So this is going to be some new identity. It will still need to have a certificate that validates the public key for that, but it doesn't need to be tied to Alice's identity in any way that's visible to anyone else. So that's the way to provide some anonymity, even though all the transactions in the network are public to everyone who participates. So this actually works. There's at least a reasonable number of people that trust this currency and are providing computation to create these blocks, which is incentivized by creating the value of new Bitcoins. There's about 9 million Bitcoins currently available. And the market price fluctuates, and it depends on the cost of computation as well as the trust in the Bitcoin network. There have been some incidents where the price fluctuated wildly because there was some concern about the security of the Bitcoin transaction site. But the current market is fairly stable, around $5 for a Bitcoin. So this is the end of Unit 6. Let me summarize what we've seen. And there are lots of connections between the different things we've seen that all use cryptography to solve problems. So the first thing we looked at was anonymous communication. And we saw how to do that using onion routing, which was a chain of public key encryptions. We looked at how to do voting using mixes, which also involved a chain of public key encryptions with the addition of audited permutations. We looked at how to provide anonymous digital cash in a centralized way. This involved using blind signatures. But blind signatures pose the risk that if you don't know what you're signing, that's a big problem. So we talked about the cut and choose technique to verify the messages before signing the one that wasn't opened. And finally, we looked at Bitcoin that provides a way to do decentralized digital cash. This also used a chain of public keys, but unlike onion routing and voting, where we were using chains of encryptions, in this case, we were using chains of signatures. And we also saw how Bitcoin uses hash preimages as a proof of work. And having proofs of work is useful for many other protocols. So all of these protocols use a combination of asymmetric cryptography and symmetric cryptography, typically involving hashing. And there's a tremendous amount of things that you can build with just these primitives. In Unit 7, we'll look at a few more interesting applications of cryptography and wrap up the course. I hope to see you there.
In this problem, we will look at a small onion network. We have a network with 5 nodes, R1 through R5, where each node has a public and private key. And so the question is, if Alice wants to send a message to Bob through our onion network, what message should she send to R1 to reach Bob? And the notation here is the notation that we've used throughout the rest of the course, where KUB is the public key of Bob, and this message is encrypted then using the public key of Bob. This question is about voting in mixed nets. Consider a mixed net with 4 non-colluding mixers and 1,000 voters. And the question is, what is the maximum number of votes that can be audited for each mixer while keeping the probability that an observer who can observe all network traffic can trace Alice's vote less than 0.001. The discussion of onion routing in lecture left out many important aspects needed for a practical and secure onion routing network. The following questions are based on this paper on Tor. A link to the paper will be included in the instructor's comments. Which of the following topics from this class are used in Tor? Counter mode encryption, cryptographic hashing, Diffie-Hellman key exchange, RSA encryption, TLS. Check all that apply. In Tor, to improve performance, instead of routing each packet using a new onion routing path, Tor sets up a circuit between two endpoints to allow further communications to only require symmetric encryption operations. And so the question is, what could go wrong? And the options are, if the onion routers at the beginning and end of the circuit collude, they are able to identify the communicating endpoints by looking at the circuit identifiers. If the onion routers at the beginning and end of the circuit collude, they may be able to identify the communicating endpoints by manipulating the timing of packets in a flow. If an onion router in the middle of the circuit is malicious, it would be able to identify and disrupt Alice's traffic by identifying the symmetric keys used. And the last option, an adversary who can cause arbitrary congestion on the network and who knows someone is sending a steady flow of packets to endpoint B may be able to identify all the onion routers in the circuit. Check all that apply. This next question asks about the handshake protocol in Tor. In the handshake protocol, which is based on the Diffie-Hellman key agreement, Alice sends Bob G of X encrypted with Bob's public key, and Bob responds with G of Y and the hash of K plus the handshake, where K is G of X of Y, which is the shared symmetric key. The question is, why does the response include the hash of K and handshake? Check all that apply. For this question, Alice has created a circuit with onion router 1 and onion router 2, and she wants to extend that to include onion router 3 and onion router 4. And the question is, how many more total messages are transmitted? Count 1 for every time a message is sent over a single hop link. To help you get started, the first two messages are Alice sends a message to onion router 1 to relay over C1, where C1 equals circuit 1, to relay on circuit 2, to extend to onion router 3, continue on with the message. Onion router 1 sends the message to onion router 2, to relay on circuit 2 to extend to onion router 3, and so on. And so how many messages do we need? On the next slide, there will be a list of threats, and we're asking you to order these by the seriousness of the threat. For the question, assume Alice is communicating with Bob using Tor and wants to keep this a secret. Alice uses the Tor protocol to set up a circuit between onion router 1, 2, and 3, and uses onion router 3 as the exit node to reach Bob. Answer by listing the letters in order from the most severe threat to the least severe. For example, DACBE, which is not the correct answer. I'll give you that one for free. Do note that some of these are subjective and multiple orderings may be considered correct. And here are the 6 threats. The first one, an attacker in the middle intercepts the relay extend request between onion router 2 and onion router 3 and attempts to set up a different Diffie-Hellman key. The second threat, a malicious attacker controls the directory server from which Alice learns the identity keys of onion router 1, onion router 2, and onion router 3. And the third threat, Alice's onion proxy is compromised. And the fourth threat, an eavesdropping attacker can observe all network traffic. And the fifth threat, onion router 1 and onion router 3 are both controlled by the same malicious attacker who has no other access to the network. And the final threat, onion router 1 and onion router 2 are both controlled by the same malicious attacker who has no other access to the network. Order these threats from the most severe to the least severe. And the answer is the first message is the only valid message. The last message is no good because it's encrypted using the public key of node 5, and so node 1 won't be able to decrypt it. The rest of these all use the public key of node 1. The third option won't work because there's only one hop. And because there's only one hop, node 1 can see that the message came from Alice and is going to Bob, and this is what we don't want a node to be able to learn. The second option won't work because after node 1, the message is directed to go to node 3, but it's encrypted using the public key of node 4. And so node 3 won't be able to decrypt the rest of this message. The first option works. It's encrypted using the public key of node 1, so node 1 can decrypt it. It's directed to send it to node 2, and it's encrypted using the public key of node 2, and so that hop will work. Node 2 is then directed to send the message to Bob, which is encrypted with the public key of Bob, so Bob will be able to decrypt the message and receive onions galore. And the answer is 177 audits. To calculate this, say we audit n votes. Then the chance of tracing Alice's vote on one mixnet is n over 1,000. And to trace it through 4 mixnets, the probability becomes n over 1,000 to the 4th power. And we want this value to be less than 1 over 1,000. Rearranging, this means we want n to be less than 1,000 to the 3/4 power, which we can calculate in Python to get 177.8. And so n equals 177. For this problem, you are asked to verify a set of blinded messages, where blinded message B equals the original message m times r, a random nonce raised to the power e, mod n. And so the question is, given the random nonce r, how do we get m from B? There are two very similar ways to accomplish this, and I'll talk about both of them. In the first way, the first step is to calculate the inverse of r mod n. And I'd like to talk for a second about what this means and how to calculate it. So in normal arithmetic, not modular, finding the inverse is easy. We can just divide by r. As a simple example, if we have 3x equals y, we can find x by dividing by 3. But with modular arithmetic, this doesn't work. Taking our same example, 3x equals y mod 5. Let's set y equals 2. If we just divide, we get x equals 2/3, which doesn't make sense. X has to be an integer. It turns out the answer is actually 4, because 3 times 4 is 12, and 12 mod 5 is 2. And so what we need to find is some z such that 3 times z is congruent to 1 mod 5. It's fairly easy to see that z equals 2 accomplishes this. 3 times 2 is 6, 6 is 1 mod 5. So going back up to our original problem, we can solve 3x is congruent to y mod 5 for x by writing x is congruent to 2y mod 5. So if y equals 2, x is 2 times 2, which is 4. And for mod 5, here are all the inverses. 1 times 1 equals 1, 2 times 3 equals 6, which is congruent to 1, 3 times 2 equals 6, which is congruent to 1, and 4 times 4 is equal to 16, which is congruent to 1. And so we can calculate inverses using the extended Euclidean algorithm, which is implemented in the PyCrypto library in crypto.util.number.inverse. So now that we have the inverse of r mod n, we can calculate our blinded message. We should calculate b to the power d, which equals m times re to the power d. And since e and d are the public and private keys of RSA encryption, we get m to the power d times r mod n. If we multiply by the inverse of r, we get md mod n. And if we apply the public exponent, we can get m. And the second way of solving this problem, first, take our random nonce to the power e, and we'll call that r. We're going to calculate the inverse of r. If we take our blinded message times the inverse of r, we get our message times re times r. Since re and capital R are inverses, they cancel, and we're left with just our message. Comparing the two ways, the second way is quicker. It only involves one exponentiation and one inverse, whereas the first way requires two exponentiations and one inverse. And here is my solution. In this first step, we calculate what I called capital R, big nonce. We use the inverse function from the PyCrypto library to calculate the inverse of our big nonce, modulus our n value. We can then remove the nonce from our bill by multiplying the bill times the nonce inverse. Again, modulus n, and returning. So in the verify function itself, we loop through all of the bills and nonces, remove the nonce, check the value, where message value does some conversions to change message, which is an integer, into bits, make sure the padding is right, and then convert the bits to a string, and then check the value of that string. We then see if the test value is equal to our target value. If it's not, return false, because we don't need to verify anymore. If we've passed all of these, return true. And the answer is all of these topics are used in Tor. Counter mode encryption is used by the cells to relay messages. Cryptographic hashing, the Diffie-Hellman key exchange, and RSA encryption are all used in cell creation and key exchange. And TLS is used by all the onion routers to maintain connections between each other. The correct answer is the second and fourth options. The first one is not an issue because the circuit identifiers are remapped in between each onion router. And so there's no way for the beginning and ends onion routers to collude. The second statement is an issue. In section 7 of Tor, the second generation onion router paper, the authors discuss this issue when talking about end-to-end timing attacks and introducing timing into messages. The third item is not an issue. Different keys are used between each router, so there is no way for a malicious router to identify and associate a key with Alice. This fourth item is an issue. To see this, let's take this example network between A and B, and we've chosen a circuit in red. An attacker could try introducing congestion on each connection, for example here, and see if it causes any disruption on the flow of packets into B. In this case it won't, and so the attacker has learned this connection is not involved. He could try here and observe, and he should see disruption of packets into B, and the attacker has learned that these two onion routers are on the circuit. He can continue on to do this on all the connections and learn which onion routers are involved. And the correct answer is the second and third options. The first one is not true. Alice can determine the key using the typical Diffie-Hellman protocol as discussed in Unit 3 by taking the value g to the power y and raising it to the power x. The fourth option is not true. Adding the hash to the message actually increases the size of it. To see why the second and third options are true, let's take a look at what could happen without including the hash. So Alice picks value x, calculates g of x, and encrypts g of x with Bob's public key. She then tries to send this to Bob. Mallory could intercept the message, and then send a different value to Bob. Bob would calculate the key, g of x prime y. Bob would then send g of y, which Mallory could intercept, and send a new value to Alice. Alice would then calculate a nonsense key and have no idea that the key that she's calculated is worthless. Adding the hash value of the key to this protocol allows Alice to verify that she has a valid key that came from Bob and not from some attacker in the middle. And the answer is 14 messages. In the first message, Alice is essentially telling Onion Router 1 to tell Onion Router 2 to extend to Onion Router 3. Then Onion Router 1 tells Onion Router 2 to extend to Onion Router 3. In the third message, Onion Router 2 tells Onion Router 3 to create a circuit. Onion Router 3 responds to Onion Router 2 saying, I've created it. Onion Router 2 responds back to Onion Router 1 saying, I've extended. And Onion Router 1 responds back to Alice saying that I've extended. To then extend onto Onion Router 4, there'll be two new messages in between Onion Router 3 and Onion Router 4. So it takes 6 messages to extend to Onion Router 3, and then 8 more messages to extend to Onion Router 4 to get 14. So as stated in the problem, some of these are subjective, but here's my answer. I believe that the most severe threat is if Alice's onion proxy is compromised. If an attacker has access to Alice's onion proxy, if Alice's onion proxy is compromised, an attacker can learn all of Alice's traffic. The least severe threat is option A. If an attacker in the middle intercepts the relay extend request between Onion Router 2 and Onion Router 3 and attempts to set up a different Diffie-Hellman key, the hash check will detect this problem. And so I think this is the least threatening. Between E and F, I think that E is more threatening than F. Having control of the entry and exit nodes is more powerful than having control of just the entry and some node in the middle. And so now we need to figure out where to put D and B. I think that D is a weaker threat than F. Just being able to observe network traffic is not very useful if you cannot correlate anything. Having control of 2 routers will give an attacker some ability to correlate traffic, perhaps through timing attacks. So D is a weaker attack than F. I think that B is a more serious threat than E. If an attacker controls the directory server, it could possibly return only nodes under its control. Then having control of 3 nodes is a more serious threat than having control of only 2 nodes. So my answer is C, B, E, F, D, and A.